Okay, yes, so this week's speaker is Peter. He's a final year PhD student from HetSys, and he's going to be talking about when the drops bounce.
Thank you very much. Yeah, so as Oscar says, I'm a student on the HetSys CDT, same as Oscar and same as student here. So there's a few of us in maths, but most of the rest of our cohorts are dispersed around the university and other science departments. So I'm working with James Brittles and Duncan Lockerbie. You might know James vaguely if you've been here for a while, but not. Duncan's in engineering, and I'm doing my PhD work looking at drop impacts. So why do we care about drops? So drops and impacts of drops are really everywhere. So they're in clouds, well, we've got water drops coming together, and if you want to get big raindrops, little drops are going to join together and create big drops. In 3D printers or inkjet printers here, we've got drops of ink. They're going to come down and hit a bit of paper, and it's useful to know whether they're going to splash or stick to the paper. What we're going to do. In certain types of combustion engines, you've got drops of fuel flying around, and you want to know whether they're going to interact and how they are going to break up or do different things. And then if you want to cool down something that's really hot, a useful technique is for spray cooling, so you fire water at a bit of hot metal, and then sort of the water will evaporate and let heat out of it, and so you want to know what's going to happen when the drops hit the bit of metal. In particular, the question I'm really thinking about is, well, when do drops merge together, or conversely, when will they not merge and pull apart? So I'm looking at sort of a few different main processes. So this is two drops of hydrocarbons, that's in fuel, and these drops are coming together, coming to hit each other, and then a very thin layer of gas gets trapped in between them, and then that gas stays there, and that means that they don't actually merge and they're able to bounce off of each other due to this very thin gas layer. And so if we want to understand this, we want to get an idea of what's actually going on inside this gas, but well, we can't see what's going on inside that. The gas is hidden by these drops. A related problem is a drop hitting a solid surface. So this is a very, very smooth solid surface, and again, a gas layer can get trapped underneath. The drops will bounce off the gas. But because it's on a solid surface, some very clever experimentalists have discovered that you can use interferometry techniques to actually measure the thicknesses of these gas films. And these get sort of nanometers or down to even micrometers or down to hundreds of nanometers thick. So very, very thin gas films compared to the size of the drops. And finally, is a sort of related problem there is what's called the Leidenfrost effect. So now this bit of metal is sort of hundreds of degrees Celsius hot, and so instead of it being sort of the ambient gas that gets trapped underneath, the drops start evaporating very rapidly, and instead they'll bounce off sort of their own evaporating vapor there. So even though that's a rough surface, these drops are actually sort of bouncing off this surface. Okay, so here's a bit of a demonstration of one very important point. So here we've got a drop that's coming down, hitting a surface and giving off a big splash. And a sort of classic thing you might think when you're doing sort of fluid dynamics is you can basically, we say, oh, we'll just ignore the gas, it's some passive gas, it's not doing anything, it's got tiny viscosity, a tiny density, it doesn't matter. But that's not always a good assumption. So these experimentalists then lowered the gas pressure and discovered that that completely stops the drop from splashing. So same gas, but changes pressure, and the behaviour of this impact changes completely. So sort of mystery, what's going on here, and the fact that suddenly the gas dynamics actually matter. Okay, so this is splashing, and I'm doing bouncing and merging, but we also have the same thing where the gas suddenly really matters to the process I'm looking at. So the sort of characteristic key thing I'm focusing on is this transitioning between whether the drops will bounce or whether they'll merge. So here we've got two drops coming together at very low speed, they come together, they deform a bit, and then the gas will escape, and then the drops will merge into a single bigger drop. If we increase the speed a bit, then the sort of transition behavior goes through what we call the soft transition. Now the drops come together a bit faster, they'll spread a bit more, the gas there can't escape fast enough, and the drops will bounce off of each other. And then if we increase the speed a bit more, another transition happens, and now the drops sort of come together so fast, the gas there gets so thin that it can sort of be punctured, and now the drops will merge together. So this is sort of very non-linear behavior that with increasing speed, first the drops are merging and then they'll bounce apart, and then if you go even faster, they'll merge together again. So what am I actually doing? So I'm sort of firmly in the computation applied maths area. So we want to write down a model which we can do, which includes all the sort of necessary physics and throws away anything that is too expensive to simulate and sort of capture what's actually going on and then do some simulations. So there's a sort of hierarchy of different models that have been used to do this. So on the one extreme, you can simulate fully the drop and the surrounding gas and fully in 3D and allow this drop all to break up, and you can do very, very expensive simulations to do this full 3D, and this will take thousands of CPU hours to do a simulation that looks like that. And then very sensible assumption to make is, okay, if we're a bit slower speeds, we can assume that this thing is actually symmetric. So we sort of assume that looking down on it, it's sort of the same in every angular direction, so you won't get these big splashes. But people can still do simulations where they simulate the gas, simulate the drop, and look at things like jetting, where it's symmetric, but you sort of have drops being set off by these impacts. And then the other extreme, very slow impacts, there's been some nice analytic work where if it's slow enough that this stays almost sort of just a small deformation from a sphere, then you can use potential flow theory and some nice analytic stuff and sort of asymptotic matching and get results for slow impacts. Now, where I sit is in this middle area where we're going to do some clever work to deal with the gas, so we don't have to simulate the entire gas domain, but I'm still going to actually solve numerically for the flow inside the drop, so we'll see a bit. So here's our drop. I'm going to talk about the model for the impact of a drop onto a hard surface, but the impact of two drops hitting head-on is almost identical. You just replace the solid surface with a symmetry condition, and it looks very, very similar. So I've got my drop here, and as I said, I'm going to assume that this thing is actually symmetric. So the drop is heading straight on down onto the surface, or I've got two drops heading head-on, and I can assume that sort of angularly it's going to look the same. And then inside the drop, these are the Navier-Stokes equations. This is sort of the classic model for an incompressible fluid. And now I'm going to solve these directly. And on the surface, we're going to have some stress due to the gas that will come to in a minute, and then the Laplace pressure, which is surface tension and sort of a surface force. But the big problem with doing these sorts of simulations, why they're so expensive normally, is that this gas layer gets ridiculously thin. So this gas layer can get down to sort of 10,000 times smaller than the radius of the drop. So if we were going to mesh the entire domain, both the sort of interior of the drop and the thickness of this gas, we'd need an absolutely tiny mesh in this thin domain, and then have a very thin mesh to track where the surface was, would just be incredibly expensive. So to get around this, we're going to use what's called lubrication theory, which you might have seen, but I'm expecting not, so I'll do a quick introduction to this. So here's a sort of thin layer of fluid, again, between, say, y0 and y some h of x, which we're going to assume we know. And then the classic equations you solve for the two velocity components of velocity in the x direction, velocity in the y direction, and the pressure of the fluid. Is that there's a big difference in our length scale, so that we've got, say, if we've got some characteristic horizontal length scale L, some characteristic vertical length scale H, and we're going to assume that this ratio of the two epsilon is very, very small. And then we're going to see what that does to our equations. So here's our horizontal Navier-Stokes equation. So if you've not seen this before, it looks scary, but it's not. It is just Newton's second law dealing with the fact that this thing is like moving. So the bit on the left-hand side is the rate of change of the velocity, so that's the change of momentum. On the right-hand side of the forces, so there's like pressure gradients, and then this one with mu is the viscosity of the fluid. So if we look at how all these different terms scale, so we're going to scale x with our long length scale, y with our short length scale, or epsilon times L. The velocities scale the same, so the horizontal velocity scales with some scale u, and the vertical one with epsilon times u, and then time with L over u, and these are what all our terms look like. And so, and we're just scaling p with some unknown pressure scale at the moment. So if we look at all these terms, they're all order 1, except for this one, because we've got epsilon squared at the bottom, so this term is big compared with the rest of these. And we've got this pressure term. So, well, we want to keep the pressure dependence on x in here, so we're going to take a pressure scale to balance this term. Pick p just so that these two terms look the same. And then all we're going to be left with is sort of the first order if we did an expansion of u into the powers of epsilon. our equations would just look like this. So we've thrown away everything except that pressure term and that large viscosity term. And we can do the same thing. So this is now the vertical momentum equation, where this is now the function and momentum going upwards. And if we do the same thing, now we can see that, okay, these are all older epsilon terms. This is epsilon to the -1, but this one is epsilon to the -3. So this pressure term here is enormous in this scale. So the only term that's going to be left of first order again is this term. So magically, in this scaling, almost all the terms have got thrown away. This is what we're left with. So if we give us some boundary conditions on U, so at the bottom, we're going to assume that we've got no slip, so there's no velocity the rest of the fluid sticks to the solid wall. And at the top, we're going to say, okay, this thing might be moving sideways with some velocity, but we're going to assume that we know that. Now this dp dy is 0, so dp dx, that doesn't depend on y. So this is just a linear second order ODE. If you stick those boundary conditions in, this is what you get. So suddenly we know what our sort of velocity profile U looks like. And then if we integrate this over y, we're going to get our volume flux. This is how much volume of fluid is moving along in this direction. And then conservation of mass, or conservation of volume, because fluid is incompressible, gives us this. So the rate of change of the height is going to be the change in the horizontal direction of this volume flux. And then if we stick this into here, we've now got 1 PdE for the pressure, but our U and V inside this fluid have disappeared. So we've gone from PdEs needing to solve for U, V, and P to just 1 for P itself. And there's now no dependence vertically in the y direction. So if we come back to our equations here, okay, so this is the axisymmetric version of this, but this is just the HDT plus the divergence of Q in these radial coordinates. And now magically, the problem we had to mesh this vertically. Now suddenly there's no vertical dependence in these equations, so we can just solve this horizontally on the base of the drop. And now we don't need to mesh across that very, very thin dimension. And then you can repeat the thing to look at what this stress to the gas does, and then that gives you this term. So this tells you how then the solution of this for the gas applies to the surface of the drop. Okay, so here's our model. We're going to solve Navier-Stokes inside the drop domain, and we're going to use lubrication theory to apply a condition just at what the gas does down here. Well, great. So you can stick this in your favorite fluid solver or PDE solver, and the drop will always bounce. So it doesn't work. So if you throw this in your code, you'll never see the merging behavior that I saw earlier. The drop will always bounce, its pressure will always get large enough that it goes away. So there's something missing here. And what's missing is that at very, very small scale, so where this gets very, very, very thin, we want some attractive force that's going to say, once it gets very close, it's actually going to get pulled in. But luckily, in the real world, such a force does exist. It's the van der Waals attraction between the two surfaces. So when these surfaces get very close, there is an attractive force between them, and it's characterized by this Hammaker constant, and you can go away and measure that from simulations or experiments not to do a drop impact, and get this as like a known constant. And now if you go back to a solver and run this at different speeds, you will see a transition with increasing speed from bouncing to emerging. So this does work, but the speeds are wrong, so it still doesn't work. So you will get a transition with this critical speed, but it won't match up with the experiments. So, okay, there's still something missing. Okay, well this time what's wrong is that I've kept saying that this thing is very, very thin, but it's a very thin layer of gas. And there's also an assumption, if you do fluid mechanics, that your length scales are much larger than sort of the intermolecular scales of the continuum. So what's actually going wrong is that we're approaching the limits of this continuum hypothesis. But we can correct for this. So here's a sort of one of those components of the lubrication equations. This is Poisson flow. So we've got a sort of parabolic profile for U, and then this is our volume flow rate. But if we correct for this, so this we're going to look at the mean free path of the gas. So this is the average distance between that a molecule will go before it hits the next molecule. So normally when you do fluid mechanics, if you're looking at, say, a bath of water, this mean free path is absolutely tiny compared with all the relevant length scales of your flow. But if you're doing gas flows, then you can actually get reasonably close. So if we say our vertical scale is still a lot larger than this mean free path, but large enough that it makes a difference, then it's been worked out that you can apply this correction, this splitting number that depends, it's this ratio of length scales, that you add a correction to this mass flow rate that accounts for the fact that this can't be assumed to be exactly zero. And then people have also looked at the other extreme. Okay, if you say you've got some rarefied gas where the gas molecules are hardly interacting, then it turns out from some pages of algebra from the Boltzmann equation that this is the form of the volume flow rate that you can get. And then doing some asymptotic fitting to some simulations of gas flow, we can come up with a correction that sort of interpolates between these two extremes. So the red dots are some simulations of the Boltzmann equation that actually give you sort of the correct results for interacting particles. And this is our correction for our flow rate. Okay, so we do the same thing. Just to put some numbers on it, the mean free path of a gas is in atmospheric pressure of air is about 70 nanometers. Experiments have seen film thicknesses down to hundreds of nanometers, so we are firmly in the regime where this ratio is no longer definitely small. Yeah, so as I say, we do these actually corrections turn up in the equations where the viscosity appears, so we can sort of think of them as like effective viscosities that depend on the height. It's not hugely important. The point is that these corrections have been included and then they work. So here's back to our equations. We've got this correction in our volume flow rate. If you non-dimensionalize, this is like a 6-dimensional problem, so there's loads of parameters going into it. But the point is now, with all of that, this works. So what am I actually doing numerically? So I'm solving inside the flow of the drop, and I'm using what's called an arbitrary Eulerian Lagrangian scheme. So I mesh the drop like this, covered it in triangles, and then you work out where your boundary is going to move with the normal velocity. Then you update the boundary, and then you smoothly interpolate the mesh to sort of keep up with the motion of the drop, and you include the right corrections to the time derivative accounts for that. My sort of simulations look like this. I'm using an open source finite element package called oomph-lib that if you want to do anything with finite elements, and it's very nice, but it's one of those packages that's written by mathematicians and you have to get deep down to the guts of the code. It's sort of one of those codes rather than something very slick and professional. So here's an experiment in the background, and then I've just overlaid the outlines of my simulation. So we've got a bouncing drop, then okay, our simulations agree very nicely. And doing the same thing with drop drop. Again, you can match up nicely with what these drops actually look like. What are some actual results? So I'm going to play you some videos of my simulations now. So if we remember back to the start where I said that there's a soft transition, that first the drops are merging, then you increase the speed a bit and then they bounce. So I've got a series of simulations at different increasing velocities. And so the slowest ones merge, you see they drop down to 0, it's the minimum height on a log scale. So this is like, here's the drops on the big scale, then I zoom in vertically, and then I'm plotting this minimum thickness between the drops here against time. We'll start playing the video. So this video is the simulation that's just above that soft transition. So this is the first time that they bounce rather than merging. So we see the drops coming together. And then even though on the macro scale you can't tell that the drop's still approaching, when you zoom in and look at what's actually going on the surface, then actually drops are approaching and closer together. You can also see that there's a gas bubble that gets trapped in between, which you can't see here. There's a big pocket of gas that's inside the drop. And then it would be here, as this gets very close together, that if it was a bit slower, they would collapse and merge together. And the drop's going to come apart. There we go. If we go up, so this is now the higher speed, so this is just before they would then merge if they were moving a bit faster. These come together and you can see they come very close, but they don't quite merge here. If they're a bit faster, this is where they merge. again, you can see there's loads of detail going on the bottom of the drops that you just can't see at sort of macroscopic scale, and so we should never see any of this behaviour in an experiment because you just can't get close to it. I'll play one more time as I have a drink. And you can see here how what's going on at the top of the drop sort of macroscopically is affecting what's going on at this edge of the film.
Sorry, can I ask a question?
Yeah.
On that thing where the top of the droplet goes down, that didn't happen on the pictures that you overlaid it on.
Yeah. So I can explain that. Let's go back a second. Which ones?
Maybe, well, I guess maybe it's really slightly on this one, but was it more obvious on the previous slide? Or yeah.
Yeah. So I've got to remember that I'm plotting. My simulations are actually axisymmetric. So my simulation domain looks like this, and so when it drops down, it looks like this. But if you're looking at it side on, if you've like spun this round, we're seeing it here from the side. This is actually this top end, so it's
Sure.
So it depends how you're plotting it. Yeah, you can't actually, again, you can't really see from the side what this is actually going as well. So,
thank you.
It's a good point. Yeah, I'm slightly cheating by plotting my simulation twice, so it looks more like a drop here, but remember that's just like spun around. Okay, so here's this set of simulations all together. So again, as I said before, we've got our sequence simulations increasing speed, and they first merge, and then they bounce and then they merge again. And I picked this particular liquid and this particular radius because this is what was looked at in a recent experimental paper, and I agree very well with the critical speeds that these transitions occur at. And these are really hard to get, basically. So you have to include both the disjoint pressure of the van der Waals force, and you have to include all those gas kinetic corrections in terms of the Knudsen number in order to get this agreement so good. If you don't include those effects, you either won't find transitions or these numbers will just be way, way off. But with these effects, you actually are able to capture these transitions. So what I've then done is I've run sort of hundreds of these simulations and then sort of plot out a phase diagram. So on the bottom, we've got the radius of the drop. Vertically, this is the velocity. And so this is then my curve. So on this side, so this bit here, this is where the drops merge for a particular velocity, a particular radius. And then on this side is where they bounce. So I've run sort of a big grid of simulations and then plotted a curve between where I see this change in behaviour. And then the blue dots is this experimental paper. And again, we're really able to capture this very well in terms of where we see these points. All the experimental data is actually reported in terms of a Weber number, which is a function of both the radius and the velocity. So if we rescale our data to sort of line up with how this experimental data it looks like, our curves tend to look like this. And if we sort of pick a particular radius and increase the speed by increasing the Weber number here, we can see the transition. We go from merging, increase a bit higher, which then bouncing, and then out again into merging again. So I can also change the gas pressure by changing the mean free path of the gas. So there have been some experiments on this using different gases and different pressures. So here's now two curves. The blue one is for sort of nitrogen or air, red one is for helium, and this side is bouncing, this side is merging. Again, nice agreement apart from this point, which we don't understand why we're not agreeing with this one at all, but there's not much data, and that's a bit of a mystery. But gas pressure actually only appears in our equations through our choice of mean free path, because we're assuming incompressible flow, so all the derivatives of pressure have disappeared, but the mean free path is inversely proportional to the pressure. So the only place that gas pressure actually appears is in this mean free path. So if we instead scale our pressure by mean free path, then this data collapses onto a single curve, which is very nice. This hasn't been realised before, so we worked this out for the first time, that all that really matters is rather than particular gas type and the particular pressure, it's all to do with this mean free path. So now I can do some nice analysis by looking at a whole grid of simulations and having a look about where they merge. So again, this region is the bouncing region, and then this is the merging region. And what I'm plotting in the colour is how far through the simulation they merge. So the dark colours means it takes longer to merge, the lighter colours means it's quicker. So you sort of see the trends you'd expect. So if you increase the speed, they're going to merge quicker. If you increase the pressure, then the pressure is stronger and they're going to merge later. And then we see down below the soft transitions in the videos I showed you earlier that it takes ages for them to merge. But there's some structure inside this, right? There's what's going on with this curve here. Clearly there's some other stuff going on. So we can also look at the radial position of contact. So now what I'm plotting is how far from the center of the drop that contact happens. So we see that there's sort of different types of contact. So this light band is where contact happens quite near the edge. This is very near the start of the impact, and contact happens close to the center of the drop. If we increase the pressure a bit, now contact happens a bit later, the drop spread a bit more, and now contact happens at this neck at the edge of the drop. And if we increase it a bit more, the drop spread much further, and there's a very strong film is formed, and we can basically get contact anywhere along this film, and it's a bit sort of random at what point, so we can get very similar simulations that either look like this or where contact happens to the back. And then down below here, contact happens right at the edge again with a big gas bubble trapped in between. So just a little bit on the drop solid impacts I mentioned earlier. So what's very nice for these impacts is that the experimenters have been able to actually measure how thick these gas films are. So this is a very recent paper where they measured the minimum thickness that the gas film got to. So this is with impact speed. So once they get past this line, they then see contact. So I also ran some simulations with the same liquid, and it looks like this. So I agree very well, again, the sort of heights at which contact starts happening. And okay, again, pretty close in terms of where I start to see contact happening. And then there was this very nice prediction of a sort of a critical film height at which this van der Waals force becomes dominant, which agrees well very nicely with my simulations, but that's not a surprise because my code is based off basically the same analysis that this critical film height was based on analysis of the model I'm using. But this critical film height agrees incredibly well with the experiments as well in terms of where they started to see contact, which is going to really nice sign that this model is sort of capturing the correct behaviour in terms of when contact starts happening. Okay, so what am I doing next? So there's a few options of things to look at. So I mentioned Leidenfrost impacts right at the start, and so you also see these sort of different types of contact behaviours for impacts where we've got evaporation going on. So there's been some simple evaporation models that have been used in the past with this setup, and I'm just going to have a look at that. Or more advanced evaporation models where if this is hot surface, and then there's heat in the bottom of the drop, but the top of the drop is cool, then you get a gradient in the surface tension because the heat decreases the surface tension, and you'll get a flow of liquid around the edge, and so might have looked at that. But what I'm actually probably going to look at for the next 6 months or so is related to the question of what happens when you have a drop hitting a liquid film. So you see in this system, we've got a thin layer of liquid, the drop's going to hit it, and you see a really similar setup of transitions between either the drop can bounce off the film or merge with it. And there have been various papers where experimentalists have used a very, very thin layer of liquid to simulate an impact onto a very smooth solid, but they don't always agree with the experiments that work on solids, and so we want to ask the question of, okay, is this thin liquid film a good substitute for a perfectly smooth solid? And if so, how thin does the film have to be before that's true? And so, okay, so just as a quick demonstration, I've just done a little 3D video of one of my simulations, and then this is lined up with that overlay I showed earlier. So yeah, as I said, I'm on the HetSys CDT. This has all been run on Warwick's great computing facilities. The code that's run all of this has been published, and I'm currently writing it up in a paper that we'll be submitting within the next couple of weeks.
So thank you very much. Any questions?